Imagine standing on a beach, watching waves roll in from the ocean. Each wave is separate, distinct, moving on its own path. Now imagine that beyond your ocean, there are other oceans, invisible to you, each with their own waves, their own rhythms. And sometimes, just sometimes, a wave from another ocean crosses over into yours, leaving a mark, a ripple, evidence that something from beyond has touched your world. This is not a story about oceans. This is a story about universes. And in the past few years, scientists have found something deeply disturbing in the data we've collected about our cosmos. They've found marks, anomalies, strange patterns in the very fabric of space and time that shouldn't be there, according to everything we thought we knew. These marks might be evidence of something extraordinary, something that challenges the very foundation of reality as we understand it. They might be bruises, scars left behind by collisions with other universes. For most of human history, we thought our universe was all there was. Earth was the center of everything, then the sun, then our galaxy, and finally we realized our universe is vast beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars. But what if even that isn't the whole story? What if our universe, as impossibly huge as it is just one bubble in an infinite foam of universes? What if there are other universes out there, existing alongside ours? And what if sometimes they touch, they collide, they leave evidence behind? This isn't science fiction anymore. This is cutting-edge cosmology, and the data coming in from our most sophisticated telescopes and experiments is disturbing scientists around the world. Today, we're going to explore this mystery together. We'll look at the evidence, examine the theories, understand what it means if universes really do collide, and confront the unsettling implications of living in a cosmos far stranger than we ever imagined. Let's start with a map. Not a map of Earth or the solar system, but a map of the entire universe when it was just a baby, only 380,000 years old. This map is called the Cosmic Microwave Background, or CMB, and it's one of the most important discoveries in all of science. The story of the CMB begins with the Big Bang. About 13.8 billion years ago, our universe began as an incredibly hot, incredibly dense point. It wasn't an explosion in space, but an explosion of space itself, expanding in all directions at once. In those first moments, the universe was too hot for atoms to form. It was a thick soup of particles and energy, completely opaque, like being inside a cloud, so dense you can't see your hand in front of your face. But as the universe expanded, it cooled. After about 380,000 years, it cooled enough for electrons and protons to combine and form the first atoms, mostly hydrogen. At that moment, something remarkable happened. Light, which had been constantly scattering off the free electrons, was suddenly free to travel through space. The universe became transparent. The light from that moment has been traveling ever since, stretched by the expansion of the universe, from visible light into microwaves, and we can still detect it today, coming from every direction in the sky. This is the Cosmic Microwave Background. It's a baby picture of the universe, a snapshot of what the cosmos looked like 13.8 billion years ago. And by studying it, we can learn about the conditions in the early universe, about how galaxies and stars and planets eventually formed, about the fundamental nature of reality itself. In 1989, NASA launched a satellite called COBE, the Cosmic Background Explorer, specifically designed to map the CMB in detail. What it found was astonishing. The CMB is incredibly uniform, almost exactly the same temperature everywhere you look, about 2.725 Kelvin, just a few degrees above absolute zero. But it's not perfectly uniform. There are tiny variations, tiny fluctuations in temperature, only about 1 part in 100,000. Some spots are slightly warmer, some slightly cooler. These tiny fluctuations are incredibly important. They represent regions where the early universe was slightly denser or slightly less dense. Over billions of years, gravity pulled matter toward the denser regions, and those regions eventually became galaxies, clusters of galaxies, the large-scale structure of the universe we see today. The fluctuations in the CMB are the seeds from which everything grew. After Hubble came more sophisticated satellites. In 2001, NASA launched WMAP, the Wilkinson Microwave Anisotropy Probe, which mapped the CMB in even greater detail. Then in 2009, the European Space Agency launched Planck, the most precise CMB mapping mission ever created. Planck measured the temperature variations in the CMB to incredible accuracy, creating a map so detailed that scientists could test fundamental theories of cosmology with unprecedented precision. And that's when things got strange. When scientists analyzed the maps from WMAP, and especially from Planck, they found anomalies, unexpected features that didn't fit the standard models. The CMB, according to theory, should have a particular statistical pattern. The hot and cold spots should be distributed randomly, following what we call a Gaussian distribution. And mostly, they are. But there are exceptions, places where the pattern breaks down, where something seems wrong. One of the most disturbing anomalies is called the cold spot. In one region of the sky, in the constellation Eridanus, there's a large area that's significantly colder than the surrounding regions. It's about 70 microkelvins colder than average, and it spans a region about 5 degrees across, which is about 10 times the width of the full moon in the sky. Now, you might think, so what? The CMB has hot and cold spots all over it. That's the whole point. But the cold spot is unusual because of its size and how cold it is. According to the standard model of cosmology, a spot this large and this cold should be extremely rare. The probability of it occurring by chance is very low, somewhere around 1 in 50 to 1 in a few thousand, depending on how you do the calculation. That's not impossible, but it's suspicious enough to make scientists uncomfortable. Another anomaly is called the axis of evil. This is not a political statement, but rather a nickname given to an unexpected alignment in the CMB. When scientists analyze the largest scale patterns in the CMB, they find that these patterns seem to be aligned with each other and with the plane of the solar system. This shouldn't happen. The CMB comes from the entire observable universe, from regions of space so distant that they couldn't have been in contact with each other. There's no reason for the patterns to align with anything, especially not with our local solar system, which is an insignificant speck in the cosmos. The alignment could be a statistical fluke, or it could be a systematic error in the measurements, something about how the satellite collects data or how we process it. Scientists have checked carefully for such errors and haven't found any convincing explanation. So the axis of evil remains a mystery, an unexplained feature in the map of creation. Then there are the hemispherical asymmetries. When you divide the CMB map into two hemispheres, you'd expect the statistics in both halves to be roughly the same, but they're not. One hemisphere has slightly larger temperature fluctuations than the other. Again, this shouldn't happen. The universe should be statistically the same in all directions, a principle called isotropy. But the data suggests it isn't perfectly isotropic. There's a preferred direction in the universe, which violates one of the fundamental assumptions of cosmology. For years, scientists have debated what these anomalies mean. Maybe they're just statistical flukes, random chance producing patterns that look meaningful but aren't. Maybe there are subtle problems with the instruments or the data analysis. Maybe our theories need small adjustments. Or maybe, just maybe, they're evidence of something far more radical. Maybe they're bruises, marks left on our universe by collisions with other universes. To understand how universes might collide, we first need to understand the concept of the multiverse. The idea that our universe might not be alone, that there might be other universes beyond our own, is ancient. Philosophers and theologians have speculated about it for centuries. But in the past few decades, the multiverse has transformed from a philosophical idea into a scientific hypothesis, one that emerges naturally from our best theories of physics. There are actually several different types of multiverses that physicists talk about, and it's important to understand the differences. The first type is the simplest. Remember that the universe is expanding, and that expansion is accelerating. This means that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. At some distance, galaxies are moving away faster than the speed of light. This doesn't violate relativity because space itself is expanding. The galaxies aren't moving through space faster than light, but space is stretching between us and them. What this means is that there's a cosmic horizon, a distance beyond which we can never see, because light from those regions will never reach us. The observable universe, the part we can see, is limited by the speed of light and the age of the universe. But beyond that horizon, space continues. There's more universe out there beyond what we can observe. In fact, if space is infinite, as many cosmologists believe, then there's an infinite amount of universe beyond our horizon. And if space is infinite and contains an infinite number of regions, like our observable universe, then something interesting happens. There are only a finite number of ways that matter and energy can be arranged within a given volume of space. It's a huge number, incomprehensibly vast, but it's finite. So if you have an infinite universe, eventually every possible arrangement must repeat. Somewhere out there, beyond countless horizons, there's another region exactly like ours, with another Earth, another you, reading these exact words. And beyond that, infinite variations on the theme, universes where history went differently, where you made different choices, where the laws of physics might even be slightly different. This is called the Level 1 multiverse, and it's the most conservative multiverse hypothesis. It doesn't require any new physics, just the assumption that space goes on forever and is roughly uniform on large scales. Then there's the Level 2 multiverse, which comes from a theory called eternal inflation. We've talked about inflation before. It's the idea that in the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion, growing from smaller than an atom to larger than a grapefruit in a tiny fraction of a second. This rapid expansion explains several puzzling features of the universe, like why it's so uniform and why space is so flat. But here's the thing about inflation. Once it starts, it's hard to stop everywhere at once. Inflation is driven by a field called the inflaton field that has a lot of energy. As space expands, this field slowly decays, losing energy and eventually stopping the inflation in that region. When inflation stops, The energy in the field is converted into matter and radiation, creating a hot, dense state that then expands and cools according to the standard Big Bang model. That's our universe. But in other regions of space, inflation might not stop at the same time. Quantum mechanics tells us that fields fluctuate randomly at small scales. In some places, these fluctuations might cause the inflated field to increase rather than decrease, causing inflation to continue in those regions. These regions expand so fast that they create more space for more fluctuations, some of which cause even more inflation. The result is a process called eternal inflation, where inflation never completely stops. It keeps creating new regions of space, new bubble universes, where inflation has ended and normal expansion takes over. Each bubble universe is like our universe, with its own Big Bang, its own galaxies and stars, possibly even its own laws of physics, if the way the inflated field decays can produce different outcomes. These bubble universes are separated by vast stretches of eternally inflating space. They're causally disconnected from each other, meaning light and information can't travel between them under normal circumstances, because the inflating space between them is expanding too fast. This is the Level 2 multiverse, a bubbling foam of universes, each one a bubble in an ever-expanding sea of inflation. And here's where things get interesting for our story. If these bubbles are constantly being created and they're expanding, eventually some of them might run into each other. They might collide. Then there's the Level 3 multiverse, which comes from quantum mechanics. This is based on an interpretation called the many worlds interpretation. In quantum mechanics, particles exist in superpositions of states until they're measured. Schrödinger's famous cat is both alive and dead until you open the box. The many worlds interpretation says that when you open the box, the universe splits into two branches. In one branch, the cat is alive. In another, it's dead. Both outcomes happen, just in different universes. Every quantum event, every moment where multiple outcomes are possible, causes the universe to branch. The result is an enormous, constantly growing tree of universes, each one representing a different sequence of quantum outcomes. This is a very different kind of multiverse from the others. These parallel universes exist in a kind of abstract quantum space, not in physical space, and they don't collide in any conventional sense. Finally, there's the Level 4 multiverse, which is more speculative and philosophical. This is the idea that every mathematically possible universe exists somewhere. If the universe is fundamentally mathematical, as some physicists believe, then every consistent mathematical structure corresponds to a real universe. This would include universes with different numbers of dimensions, different laws of physics, different fundamental constants. It's the ultimate multiverse, encompassing not just everything that does exist, but everything that could exist. For our purposes, the most relevant is the Level 2 multiverse, the bubble universes created by eternal inflation. Because if these bubbles exist and they're expanding, the question naturally arises, can they collide? And if they do, what would it look like? What evidence would they leave behind? To understand how universes might collide, we need to think carefully about what these bubble universes actually are and how they behave. Imagine blowing bubbles with a bubble wand. Each bubble is separate, enclosed by a thin film of soap. The bubbles expand as you blow air into them, and if two bubbles touch, their films merge, creating a shared boundary between them. Bubble universes are similar in some ways, but different in crucial details. Each bubble universe is a region where inflation has stopped. Inside the bubble, space is expanding, but at a much slower rate than the eternally inflating space outside. The boundary of the bubble, often called the bubble wall, is moving outward at very close to the speed of light, expanding into the inflating region around it. Now, here's the key point. These bubbles are forming constantly in the eternally inflating space, and they're all expanding outward at nearly the speed of light. So if two bubbles form near each other in the inflating space, their expanding walls will eventually meet. When they do, they collide. What happens during the collision depends on the details of the physics, which we don't fully understand. But we can make some educated guesses based on our theories. When two bubble walls collide, they can't pass through each other. Instead, they merge, creating a boundary between the two bubble universes. This boundary is a region of intense energy, where the fields that define each universe interact. The collision releases energy, possibly a lot of it. This energy propagates through each universe as a shock wave, traveling outward from the point of collision at the speed of light. The shock wave carries a distinctive pattern, a signature that depends on the properties of the colliding bubbles and the physics of the bubble walls. If our universe has been struck by another bubble universe, that collision would have happened early in our history, perhaps even before observable universe had finished forming. The shock wave from the collision would have affected the distribution of matter and energy in the early universe, leaving an imprint on the cosmic microwave background. What would that imprint look like? Theoretical physicists have calculated what we should expect. The signal would be a circular pattern on the CMB map, a disk where the temperature fluctuations are different from the surrounding regions. The disk would be centered on the direction of the collision. Inside the disk, the temperature might be slightly higher or slightly lower than average, depending on the details. The boundary of the disk would be marked by a ring where the temperature changes more sharply. The size of the disk depends on when the collision happened and how far the shock wave had traveled through our universe by the time the CMB was emitted. If the collision happened very early, the disk could be quite large, possibly covering a significant fraction of the sky. If it happened later, the disk would be smaller, but the signal might be stronger. Multiple collisions are possible. If our bubble universe has been bumped by several other bubbles during its history, we might see multiple disks on the CMB map, each one representing a different collision event. The disks could overlap, creating complex patterns. This is testable. We have detailed maps of the CMB from satellites like WMAP and Planck. If there are circular patterns in those maps that match the predictions for bubble collisions, that would be evidence, possibly the first direct evidence, that other universes exist and that they've collided with ours. Scientists have looked, and what they've found is intriguing, puzzling, and yes, somewhat disturbing. In 2010, a team of physicists led by Stephen Feeney, then a graduate student at University College London, decided to search for the signature of bubble collisions in the CMB data. They developed sophisticated algorithms to scan the maps from the WMAP satellite, looking for the circular patterns that would indicate a collision. The search was challenging. The CMB is full of temperature variations, and many patterns can look circular just by chance. The researchers had to carefully account for the statistical properties of the CMB, the noise in the measurements, and the many other effects that can create patterns in the data. They needed to distinguish real collision signatures from false alarms. After months of analysis, they announced the results, and the findings were striking. They had found several candidate collision signatures, circular regions in the CMB that matched the expected pattern. 4 of the candidates were particularly interesting, with statistical significance high enough that they were unlikely to be random fluctuations. The probability of all 4 appearing by chance was low, perhaps around 1 in several thousand. The announcement created a sensation in the physics community. If confirmed, this would be one of the most important discoveries in the history of science, direct evidence of other universes. It would validate the idea of eternal inflation and the multiverse. It would open up entirely new areas of research, and it would fundamentally change our understanding of reality. But science doesn't work by announcements. It works by replication, verification, and skepticism. Other teams immediately began checking the work. They reanalyzed the data using different methods. They looked for systematic errors, alternative explanations, anything that might cast doubt on the collision hypothesis. Some researchers found problems. They argued that the candidates' signatures weren't as statistically significant as claimed. They showed that similar patterns could arise from the way the data was processed, or from known features in the CMB, like the cold spot that we discussed earlier. They suggested that the researchers were seeing patterns where none existed, a problem called apophenia, the tendency of the human mind to find meaningful patterns in random data. Feeney and his colleagues responded to the criticisms, refining their analysis, addressing the concerns. The debate went back and forth, as it does in science when dealing with subtle signals in noisy data. No consensus was reached. The evidence was tantalizing, but not conclusive. Then, in 2013, the Planck satellite released its detailed map of the CMB with much higher resolution and sensitivity than WMAP. If the collision signatures were real, they should be even clearer in the Planck data. Researchers rushed to analyze the new data, searching for the telltale circular patterns. The results were mixed. Some of the candidate collisions from the WMAP analysis seemed to be confirmed in the Planck data. Others disappeared or became less significant. New candidates emerged. The overall picture was murky, frustrating. There was something there, something unusual in the data, but it was hard to pin down exactly what it was. A team led by Rangaram Cherry at the California Institute of Technology took a different approach. Instead of looking for circular patterns, they looked for a more subtle signal. They examined the overall brightness of the CMB in different regions of the sky, looking for areas that were consistently brighter or dimmer than expected. In 2015, Cherry announced that he had found such a region, a large patch of sky where the CMB was about 4,500 times brighter than it should be. This was weird, really weird. The excess brightness couldn't be explained by normal astrophysical processes. Cherry suggested that it might be a signal from another universe, not from a collision, but from some kind of leakage or entanglement between our universe and a neighboring one. The idea was highly speculative, and many scientists were skeptical. But the anomaly was real. Something was making that region of the sky brighter than expected. Other anomalies have been found as well. We mentioned the cold spot earlier. Some researchers have suggested that the cold spot might be evidence of a bubble collision, a region where our universe was struck by another, leaving a cold imprint on the CMB. Alternative explanations exist, like a supervoid, a large empty region of space between us and the CMB that might cause light to lose energy as it passes through, making the CMB appear colder. But the supervoid explanation has problems too, and the debate continues. Then there are the hemispherical asymmetries. The fact that one half of the sky looks statistically different from the other. Could this be evidence that our entire observable universe is offset from the center of our bubble universe? That we're closer to one edge than the other? If so, we might see asymmetric effects from collisions that happened on one side of the bubble. The point is this: there are multiple anomalies in the CMB data, features that don't quite fit the standard model of cosmology. Any one of them might be a statistical fluke or a measurement error, but taken together, they paint a picture of a universe that's more complex, more strange than we thought. And the bubble collision hypothesis provides a framework that could potentially explain several of these anomalies at once. But we need to be careful. Science has a long history of false alarms, cases where unusual data turned out to have mundane explanations. The cosmos is full of surprises, and our theories are incomplete. Just because we can't explain something with our current models doesn't mean we need to invoke other universes. Extraordinary claims require extraordinary evidence, and the evidence for bubble collisions, while intriguing, is not yet extraordinary. Let's focus more closely on the cold spot, because it's one of the most thoroughly studied anomalies and one of the best candidates for a bubble collision signature. The cold spot was first noticed in the WMAP data and confirmed by Planck. It sits in the constellation Eridanus in the southern celestial hemisphere. It's not just a small cool patch, but a large void, roughly circular, about 10 degrees across on the sky. The cold spot is puzzling for several reasons. First, as we mentioned, it's statistically unlikely. The probability of such a large, cold region appearing by chance in the CMB is low. Second, it's not the only odd feature in that region of the sky. Surrounding the cold spot is a pattern of smaller cold and hot spots that also seems unusual. The overall structure looks like a target, with the cold spot at the center and rings around it. This pattern is reminiscent of what you'd expect from a shock wave, like ripples spreading outward from where a stone hits water. In 2013, astronomers decided to look at what's in the direction of the cold spot, not at the CMB itself, but at the distribution of galaxies along that line of sight. If there's a large void in space between us and the CMB in that direction, it might explain the temperature anomaly. Light from the CMB would have to pass through the void, and according to a phenomenon called the integrated Sachs-Wolf effect, photons lose energy when they pass through voids, making the CMB appear cooler. They found something surprising. There is indeed a void in that direction, but it's not large enough or empty enough to explain the cold spot on its own. The void is about 1 billion light years across, which is big but not unprecedented. And it's not completely empty. It just has fewer galaxies than average. The calculations showed that this void could account for only about 10% of the cold spot's coldness. The rest remains unexplained. So the mystery deepened. If it's not just a supervoid, what is it? Some researchers have suggested that it might be a combination of factors, a void plus some unusual properties in the CMB itself. Others have proposed more exotic explanations, like a cosmic texture, a defect in the fabric of space-time left over from the early universe. And then there's the bubble collision hypothesis. If the cold spot is the scar of a collision with another universe, it would make sense that there's also a void there. The collision would have affected the distribution of matter in the early universe in that region. It might have created a region that was less dense, which over billions of years would have evolved into a void with fewer galaxies. So the cold spot and the supervoid might both be consequences of the same event, a collision that happened in the first moments of our universe's existence. To test this idea, researchers have been running computer simulations. They model what would happen if our universe collided with another bubble universe early in its history. They simulate how the shock wave would propagate through space, how it would affect the distribution of matter and energy, how it would imprint itself on the CMB, and how the resulting structure would evolve over billions of years to the present day. The simulations are incredibly complex, requiring supercomputers to calculate the evolution of billions of particles following the laws of physics. But they're necessary because we can't do experiments with universes. We can't create a bubble collision in a lab and watch what happens. All we can do is simulate and compare the results with observations. The results of these simulations are intriguing. They show that bubble collisions can indeed create features like the cold spot, large regions that are colder than average, surrounded by rings of temperature variations. They also show that the collision affects the distribution of matter, potentially creating voids. The simulations don't prove that the cold spot is from a collision, but they show that it's consistent with that hypothesis. However, the simulations also show that other explanations are possible. The universe is full of random fluctuations, and sometimes rare events happen. Maybe the cold spot is just bad luck, a 1 in 1,000 chance occurrence that we happen to observe. Or maybe there's some aspect of the physics of the early universe that we don't understand, some process that can create features like the cold spot without invoking other universes. This is where science gets difficult. We have a mystery, multiple possible explanations, and limited data. We can't easily get more data because the CMB is a one-time event. We have the maps we have, and while future satellites might measure the CMB with even greater precision, the fundamental information is already there. We're not going to discover something completely new in the CMB. We can only refine our understanding of what's already visible. So scientists are looking for other ways to test the collision hypothesis. They're examining the polarization of the CMB, the way the light waves are oriented, which carries additional information about the early universe. They're looking at the distribution of galaxies and the large-scale structure of the cosmos, searching for patterns that might have been influenced by a collision. They're developing more sophisticated statistical methods to tease out subtle signals from the noise. And they're waiting, hoping that future observations, perhaps from entirely different types of experiments, will provide the key to solving the mystery. Let's think more deeply about what actually happens when two universes collide. It's not like two objects bumping into each other in the usual sense. These aren't solid things. They're regions of space-time, each one a separate cosmos with its own space, time, matter, and energy. So what does it mean for them to collide? Remember that each bubble universe is expanding. The bubble wall, the boundary between the inside of the bubble where normal expansion is happening and the outside where eternal inflation continues, is rushing outward at nearly the speed of light. From inside the bubble, if you could somehow see the wall, it would look like a vast barrier approaching you at almost the fastest speed allowed by physics. When two bubble walls meet, they can't pass through each other. The physics of the inflattened field that creates the bubbles doesn't allow it. Instead, the walls merge, forming a boundary surface between the two bubbles. This boundary is a place of extreme physics, where the properties of both universes meet and interact. The energy density at the boundary can be enormous, comparable to or even exceeding the energy densities in the early moments of each universe after inflation ended. This energy has to go somewhere. It gets converted into particles and radiation creating a fireball at the collision site. From inside each bubble universe, this looks like a shockwave, a sudden influx of energy rushing inward from the direction of the collision. The shockwave travels at the speed of light, spreading through the universe, carrying the signature of the collision. Everything in its path is affected. Matter gets pushed around. The fabric of space-time ripples. The temperature increases slightly, and these effects leave permanent imprints on the structure of the universe. Now, here's a crucial point. If the collision happened early in our universe's history, before the CMB was emitted, the shock wave would have passed through the entire observable universe by now. We would be living inside the collision scar. Everything around us, every galaxy, every star, every atom, would have been affected by the collision in some way. But the effects would be subtle. The collision doesn't destroy the universe or drastically alter the laws of physics. It's more like a perturbation, a deviation from what would have happened if there had been no collision. Regions affected by the shock wave might have slightly different densities, slightly different temperatures, slightly different expansion rates. Over billions of years, these tiny differences get amplified by gravity and cosmic evolution, creating observable effects in the present day. If the collision happened more recently, or if it struck only part of our observable universe, we might see a more localized signal. There would be a direction in the sky from which the shock wave came, and effects would be strongest in that direction. This is what researchers are looking for when they search for circular patterns in the CMB. But there's another possibility, and it's more disturbing. What if we're not just talking about one collision, but many? What if our bubble universe has been struck multiple times by neighboring bubbles? Each collision would leave its own signature, its own set of effects. And if the collisions happened at different times and from different directions, the resulting patterns would be complex, overlapping, possibly difficult to disentangle. This scenario seems increasingly plausible as we learn more about eternal inflation. If inflation is truly eternal, bubbles are forming constantly, everywhere in the inflating space. Our bubble is expanding, but so are countless others. Collisions should be common, not rare. In fact, some theoretical calculations suggest that most bubble universes should experience multiple collisions during their history. If that's true, then the anomalies we see in the CMB might not be from one collision, but from several. The cold spot might be one collision. The hemispherical asymmetry might be from another, or from the cumulative effect of multiple collisions on one side of the sky. The axis of evil might be yet another collision, or an artifact of how the different collision signals combine. This makes the analysis even more complicated. Instead of searching for one circular pattern, we need to search for multiple overlapping patterns, each one potentially having different properties. It's like trying to hear individual conversations at a loud party. The signals get mixed together, and separating them requires sophisticated methods and a lot of data. And then there's an even more disturbing thought. What if a collision happens not in our past, but in our future? What if, right now, another bubble universe is expanding toward us, and we're on a collision course? What would happen when the shock wave hits? The answer depends on the details of the collision, which we can't predict because we don't know the properties of the other universe. But in principle, a collision could be catastrophic. The shock wave could disrupt the structure of our universe, tearing apart galaxies, extinguishing stars, even altering the laws of physics in unpredictable ways. Or it could be gentle, a mild perturbation that we'd barely notice. Some theoretical models suggest that collisions can trigger the decay of the vacuum state of a universe. Our universe exists in a particular energy state, and it's possible that this state is not the lowest possible energy, just a local minimum. It's like a ball sitting in a shallow valley on a hillside. It's stable as long as nothing disturbs it, but a big enough push could send it rolling down to a lower valley. A collision could provide that push, causing our universe's vacuum to decay into a lower energy state. If that happens, a bubble of the new vacuum state would form and expand outward at the speed of light, converting everything it touches. The laws of physics inside the bubble would be different, and all existing structures would be destroyed. This is called vacuum decay, and it's one of the more terrifying scenarios in theoretical physics. The good news is that we have no evidence it's happening. Our universe seems stable, but the possibility exists, lurking in the equations, a reminder that we live in a cosmos that's far more fragile and strange than everyday experience suggests. In 2009, the European Space Agency launched the Planck satellite, the most advanced instrument ever built for studying the cosmic microwave background. Planck was designed to measure the temperature of the CMB with unprecedented precision, mapping the tiny fluctuations across the entire sky at multiple frequencies. The goal was to answer fundamental questions about the universe. How old is it exactly? What's it made of? How did structure form? And what do the anomalies in the CMB really mean? Planck operated for 4 years, collecting data continuously. In 2013, the Planck team released their first full sky map of the CMB, and it was spectacular. The detail was breathtaking, far surpassing previous missions. Every feature, every hot spot and cold spot was captured with exquisite clarity. Scientists around the world eagerly began analyzing the data, looking for answers to the mysteries that had puzzled them for years. What they found was both reassuring and deeply puzzling. On one hand, the data confirmed the standard model of cosmology, called lambda-CDM, with remarkable precision. The universe is 13.8 billion years old, give or take a few tens of millions of years. It's made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. Space is flat, or very nearly so. The tiny fluctuations in the CMB follow the predicted pattern, at least on most scales. But on the other hand, the anomalies persisted. The cold spot was still there, still inexplicably cold. The hemispherical asymmetry was confirmed, with one half of the sky showing larger temperature variations than the other. The axis of evil remained, with the largest scale patterns still mysteriously aligned. And new anomalies emerged as researchers dug deeper into the data. One of the most puzzling new findings was related to the power spectrum of the CMB. The power spectrum is a way of breaking down the temperature fluctuations by scale, measuring how much variation there is at different angular sizes on the sky. Theory predicts what this power spectrum should look like based on the conditions in the early universe. And for most scales, the data matched the predictions beautifully. But at the largest scales, something was wrong. The amount of variation was less than expected. The universe seemed smoother on large scales than it should be. This discrepancy had been hinted at in earlier data, but was now confirmed by Planck with high confidence. It's called the low L anomaly, where La refers to the multipole moment in the mathematical expansion of the CMB temperature field. Large scales correspond to low values of L. Why would the universe be smoother than expected at large scales? Several explanations have been proposed. Maybe something about the inflation process was different than we thought. producing less variation at large scales. Maybe the universe is finite rather than infinite, and we're seeing an edge effect. Or maybe, once again, we're seeing the influence of something from outside our bubbled universe, an interaction with the larger multiverse that suppresses variations at the largest scales. Another intriguing finding from Planck was related to the lensing of the CMB. As light from the CMB travels through the universe toward us, it passes through gravitational fields created by galaxies and clusters of galaxies. These gravitational fields bend the light slightly, an effect called gravitational lensing. By studying the distortions in the CMB, researchers can map the distribution of matter along the line of sight, creating a three-dimensional picture of the universe's structure. Planck measured this lensing signal with high precision, and it was mostly consistent with expectations. But there were some odd features. In certain directions, the lensing was stronger or weaker than expected based on the visible matter. This could be evidence of additional structures, perhaps enormous voids or superclusters that we haven't mapped yet. Or it could be something more exotic, like effects from neighboring universes exerting gravitational influence on our own. The Planck team also looked for non-Gaussianity in the CMB, deviations from the expected Gaussian distribution of temperature fluctuations. The simplest models of inflation predict that the fluctuations should be Gaussian, meaning they follow the familiar bell curve distribution. But some more complex models predict deviations, non-Gaussian features that would tell us about the details of the inflation process. Planck found hints of non-Gaussianity, but the signals were weak and not statistically significant enough to draw firm conclusions. The universe seems mostly Gaussian, but there are tantalizing hints that something more complex might be going on. And some of those hints, again, are consistent with what you'd expect from bubble collisions, which should produce non-Gaussian features in the regions they affect. All of this data has been analyzed and reanalyzed by hundreds of researchers using different methods and approaches. Papers have been published, debated, critiqued, and refined. And the overall picture that emerges is one of a universe that mostly fits our theories, but has enough odd features, enough unexplained details to keep scientists up at night wondering what they mean. The most conservative interpretation is that these are just statistical fluctuations or subtle systematics that we haven't fully understood. The universe is complicated, and our measurements are not perfect. Maybe with better data or better analysis techniques, the anomalies will go away or find mundane explanations. But there's another interpretation, one that's more exciting and more disturbing. Maybe the anomalies are real. Maybe they're telling us something profound about the nature of reality. Maybe we live in a multiverse, and our universe bears the scars of collisions with its neighbors. Maybe the cosmos is far stranger, far more vast, far more interconnected than we ever imagined. As evidence for anomalies in the CMB has accumulated, physicists have proposed numerous theories to explain them. Some are conservative, requiring only small modifications to existing models. Others are radical, demanding complete rethinking of cosmology. Let's explore some of the leading contenders and understand what they predict and how they could be tested. First, there's the null hypothesis. Nothing unusual is happening. The anomalies are statistical flukes, random patterns that happen to look significant, but actually aren't. When you analyze enough data, looking for enough different kinds of patterns, you're bound to find some things that seem unusual just by chance. This is called the look elsewhere effect, and it's a serious concern in any statistical analysis. Researchers try to account for this by carefully calculating probabilities and significance levels. They use techniques like Bayesian analysis and cross-validation to ensure their findings are robust. But there's always uncertainty. Maybe the cold spot is just a 1 in 1,000 chance occurrence, and we happen to observe it. Maybe the hemispherical asymmetry is a subtle artifact of how we define our coordinate system, or how we remove foreground contamination from the data. This explanation is boring, but we can't rule it out. Science demands that we remain skeptical and consider mundane explanations before leaping to exotic ones. However, as more anomalies are found, and as they persist in better data, the null hypothesis becomes increasingly strained. At some point, you have to ask, how many coincidences are we willing to accept? Second, there are modifications to the inflation model. The simplest models of inflation predict a nearly Gaussian, nearly scale-invariant distribution of fluctuations. But there are many ways to modify inflation while keeping its basic features. You can add multiple inflaton fields, create models where inflation happens in stages, include interactions between the inflaton and other fields, and so on. Some of these modified inflation models predict anomalies like the low L problem or hemispherical asymmetries. For example, if the inflaton field had a slight gradient across the region that became our observable universe, that could create an asymmetry. Or if inflation ended slightly differently in different regions, that could create large-scale patterns. These models are worth exploring, and many physicists are working on them. But they face a challenge. They need to be specific enough to make testable predictions, but general enough to explain all the different anomalies. It's easy to construct a model that explains one anomaly, but hard to explain several at once without the model becoming contrived or fine-tuned. Third, there's the possibility of topological defects. In the early universe, as it cooled and went through phase transitions, defects might have formed in the fabric of spacetime. These are analogous to the defects that form in crystals or the vortices that form in superfluids. Cosmic strings, domain walls, and monopoles are examples of such defects. Some of these defects, particularly cosmic textures, could leave imprints on the CMB that look similar to the observed anomalies. A texture is a knot in a field that can't be smoothly untangled. If such a texture existed in the region that became our observable universe, it could create a cold spot or other features in the CMB. The texture hypothesis for the cold spot has been investigated, and it's not ruled out. But textures are predicted by certain theories, but not by others. And we have no independent evidence that they exist. So this explanation, while possible, is somewhat ad hoc. Fourth, there's the bubble collision hypothesis, which we've been discussing throughout this story. This explanation has the advantage of being a natural consequence of eternal inflation, a theory that many cosmologists already find compelling for other reasons. If eternal inflation is correct, bubble collisions should happen, and they should leave signatures in the CMB. The challenge is that the exact signature depends on many details: the properties of the colliding bubbles, the physics of the bubble walls, the angle and timing of the collision, and so on. There's a lot of freedom in the models, which makes it hard to make definitive predictions. But researchers have been working to narrow down the possibilities and make the predictions more specific. One promising approach is to combine observations from the CMB with other data sources. If a bubble collision affected our universe, it should influence not just the CMB, but also the distribution of galaxies, the properties of the dark matter halo, maybe even the gravitational wave background. By looking for correlated signals in multiple datasets, researchers can build a stronger case. Fifth, there are more exotic possibilities. Some physicists have proposed that the anomalies might be evidence of quantum entanglement between our universe and others, creating subtle correlations that we can detect in the CMB. Others have suggested that they might be remnants of a previous universe that existed before the Big Bang, imprints carried through a cyclic process where universes are born, die, and are reborn. There's also the controversial idea that our universe might be a simulation, and the anomalies are glitches or artifacts of the computational process. This idea is fun to think about, but notoriously hard to test scientifically, since any test we can imagine could, in principle, be part of the simulation. The point is that we're not short on ideas. The challenge is distinguishing between them. We need more data, better analysis techniques, and clever experiments that can rule out some possibilities while supporting others. Science progresses not by proving theories true, but by proving them false, eliminating explanations that don't fit the evidence until, ideally, only one remains. There's another piece of the puzzle that we haven't fully explored yet: dark energy. Remember that dark energy is the mysterious force causing the expansion of the universe to accelerate. It makes up about 68% of the total energy density of the universe, yet we don't know what it is. And interestingly, there might be a connection between dark energy and the multiverse, including the possibility of bubble collisions. In many models of eternal inflation, the inflattened field that drives inflation is related to the vacuum energy of space. When inflation ends in a bubble, the vacuum transitions from a high energy state to a lower energy state. But lower doesn't necessarily mean zero. There could still be residual vacuum energy left over, and this leftover energy would act like a cosmological constant, causing the universe to accelerate. This provides a natural explanation for why dark energy exists. It's the residual energy from the end of inflation. Different bubbles, depending on exactly how inflation ends in each one, would have different amounts of residual vacuum energy. This means different bubble universes would have different values of the cosmological constant, different amounts of dark energy. Now, here's where it gets interesting. If two bubbles with different vacuum energies collide, the collision zone becomes a place where the properties of space are changing. The vacuum energy might be higher or lower in the region affected by the collision. This could create observable effects. One possibility is that the collision alters the expansion rate of our universe in the affected region. If the shock wave from the collision carried higher vacuum energy, that region might be expanding faster than average. If it carried lower vacuum energy, it might be expanding slower. These differences would be small, but potentially measurable. Astronomers have recently been grappling with a puzzle called the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding. But when we measure this constant using observations of the early universe, specifically the CMB, we get a different answer than when we measure it using observations of the late universe, like distances to supernova and galaxies. The difference is small, only about 9%, but it's statistically significant and has persisted despite careful checks of the measurements. What if the Hubble tension is evidence of a bubble collision? If a collision affected part of our observable universe, changing the expansion rate in that region, it could create the discrepancy we observe. Measurements that sample different parts of the sky or different distances might be seeing slightly different expansion rates, leading to different values of the Hubble constant. This is speculative, and most astronomers favor more mundane explanations for the Hubble tension, like systematic errors in the measurements or small misunderstandings in the models. But the multiverse explanation can't be ruled out yet, and some researchers are taking it seriously. There's another connection to dark energy through the anthropic principle. The amount of dark energy in our universe seems finely tuned. If it were much larger, it would have prevented galaxies and stars from forming, making the universe empty and lifeless. If it were zero or negative, the universe might have collapsed long ago. The value we observe is just right for life. Why? One explanation is the multiverse. If there are countless bubble universes, each with different values of the vacuum energy, then we naturally find ourselves in one where the value allows for galaxies, stars, planets, and life. We couldn't exist in universes where the dark energy is too large or too small, so we don't observe those values. This is called anthropic selection. The anthropic principle is controversial. Some physicists love it because it explains otherwise inexplicable fine-tunings. Others hate it because it seems like giving up, admitting we can't explain why the constants have the values they do. But if the multiverse is real, anthropic reasoning might be unavoidable. We might have to accept that some properties of our universe are the way they are, simply because we couldn't observe them being any other way. And if bubble collisions are real, they might give us a way to test this. Different bubbles have different vacuum energies. If our bubble has collided with another that has a very different vacuum energy, the collision zone might have properties incompatible with life. We wouldn't exist in that zone, but we might observe it as a peculiar region of the sky with strange properties. This could be another signature to search for in the data. So far, we've focused on the cosmic microwave background as the main source of evidence for bubble collisions. But there's another way to search for signs of the multiverse: gravitational waves. These ripples in space-time, predicted by Einstein's general relativity and first directly detected in 2015, open up an entirely new window on the universe. Gravitational waves are produced by accelerating masses, particularly by violent events like merging black holes, colliding neutron stars, or supernova explosions. But they can also be produced by processes in the early universe, including inflation and potentially bubble collisions. During inflation, quantum fluctuations in the fabric of space-time itself get amplified, creating a background of gravitational waves. These primordial gravitational waves would fill the universe, carrying information about the conditions during inflation. Detecting them would be a major triumph, confirming inflation and telling us about the energy scale at which it occurred. If our universe collided with another bubble, the collision should also produce gravitational waves. The shock wave traveling through space would create ripples in space-time, a burst of gravitational waves emanating from the direction of the collision. These waves would be different from the smooth background from inflation, having a distinctive pattern that depends on the properties of the collision. Current gravitational wave detectors, like LIGO and Virgo, are sensitive to high-frequency waves from relatively nearby sources, like merging black holes. They're not sensitive enough to detect the primordial gravitational waves from inflation or bubble collisions, which would have much lower frequencies. But future detectors might be able to. The Laser Interferometer Space Antenna, or LISA, is a planned space-based gravitational wave observatory that will be sensitive to lower frequencies. Scheduled to launch in the 2030s, LISA will consist of 3 spacecraft flying in formation, separated by millions of kilometers, using lasers to measure tiny changes in the distances between them caused by passing gravitational waves. LISA could detect gravitational waves from the early universe, including those from bubble collisions. If our universe was struck by another bubble, Lisa might see a directional signal, gravitational waves coming preferentially from one part of the sky. This would be powerful evidence, complementing what we see in the CMB. There's also the possibility of detecting gravitational waves indirectly through their effect on the polarization of the CMB. Gravitational waves twist the polarization of light, creating a particular pattern called B-mode polarization. Several experiments, including ground-based telescopes in Antarctica and balloon-borne instruments, are searching for this signal. So far, B-mode polarization from primordial gravitational waves has not been detected. Although there was a false alarm in 2014, it generated a lot of excitement before being debunked. The non-detection places limits on the energy scale of inflation and rules out some models. But the search continues with increasingly sensitive instruments. If B-mode polarization is eventually detected, it will not only confirm inflation, but also potentially reveal details about the multiverse. Different inflation models predict different levels of gravitational waves. Models with bubble collisions might predict additional features in the B-mode pattern, asymmetries or localized enhancements that could be distinguished from the smooth background predicted by simple inflation models. Another intriguing possibility involves the stochastic gravitational wave background, a sea of overlapping gravitational waves from countless sources throughout the history of the universe. This background is being searched for by pulsar timing arrays, networks of precisely monitored millisecond pulsars spread across the galaxy. Gravitational waves passing through the galaxy affect the timing of the pulses in a correlated way that can be detected. In 2023, multiple pulsar timing array projects announced evidence for a gravitational wave background at very low frequencies. The signal is consistent with gravitational waves from supermassive black hole mergers, but other sources can't be ruled out yet. Some physicists have speculated that the signal could include contributions from the early universe, possibly even from bubble collisions or other multiverse phenomena. It's too early to tell. The signal is just at the threshold of detection, and more data is needed to characterize it properly. But the fact that we're now able to detect such faint signals at all is a testament to the power of modern observational techniques. We're entering an era where the multiverse might be accessible to empirical investigation, where we can go beyond theoretical speculation and actually test whether other universes exist. If it turns out that universes really do collide, and that our universe bears the scars of such collisions, what does that mean? What are the implications for science, for philosophy, for how we understand our place in the cosmos? Let's explore some of the profound consequences. First, it would confirm the multiverse. The existence of other universes, other realms of space and time beyond our own, has been a theoretical possibility for decades. But without evidence, it remains speculation, philosophy rather than science. Direct detection of collision signatures would change that. It would transform the multiverse from an untestable idea into an established fact. Other universes exist. We're not alone, not in the sense of other civilizations, but in the even more fundamental sense of other realities. This would be one of the greatest discoveries in the history of science, comparable to the Copernican revolution, when we realized Earth isn't the center of the universe, or to the discovery of galaxies beyond the Milky Way. Each of these discoveries expanded our conception of reality, showing us that we're part of something much larger than we thought. The multiverse would be the ultimate expansion, revealing that even our universe, vast as it is just one bubble in an infinite sea. Second, It would tell us about the physics of the very early universe. Bubble collisions happen during or shortly after inflation. By studying the signatures they leave behind, we can learn about the inflaton field, the energy scales involved, the dynamics of how inflation ends, and how universes are born. This is physics at energies far beyond anything we can create in particle accelerators, physics that we can only access by studying the cosmos itself. Understanding inflation is crucial because it sets the initial conditions for everything that comes after. The properties of the inflaton field determine the density fluctuations that seed galaxy formation, the amount of dark matter and dark energy, possibly even the values of fundamental constants. If we can pin down the details of inflation through collision signatures, we'll understand why our universe has the properties it does. Third, it might help us understand the fine-tuning problems. Many properties of our universe seem finely tuned for life. The strength of gravity, the masses of fundamental particles, the amount of dark energy. If any of these were significantly different, stars couldn't form, atoms wouldn't be stable, or the universe would be empty. Why are the values just right? The multiverse offers an answer. There are countless universes with different values, and we find ourselves in one where the values allow for life because we couldn't exist in the others. If bubble collisions are real, it strengthens this argument. Each bubble universe is a separate experiment, trying out different values, and the properties of each bubble are determined by the random quantum fluctuations during inflation. We observe the values we do because of anthropic selection. Not everyone likes this answer. It seems to replace the question, why are the constants this value? With, because they have to be for us to be here, which feels unsatisfying. But if it's true, we might have to accept it. Some questions might not have deeper answers. Fourth, it raises the possibility of future collisions. If our universe has been struck in the past, could it happen again? Are there other bubbles out there, expanding toward us on a collision course? And if so, when would we know? Could we see it coming? The answers depend on the details. In most models, once eternal inflation is far from a bubble, collisions become less likely as time goes on because the inflating space between bubbles is expanding faster than the bubbles themselves. But it's possible, depending on the geometry and dynamics, that collisions could happen at any time. If another bubble is approaching, we wouldn't know until the shock wave hits us, because the wall is moving at the speed of light. There'd be no warning. What would happen? In the best case scenario, the collision would be gentle. A mild perturbation, it creates interesting effects in the sky but doesn't harm us. In the worst case, it could be catastrophic, disrupting the structure of space, triggering vacuum decay, ending our universe as we know it. Most physicists think the catastrophic scenarios are unlikely, but we can't rule them out completely. We live in a universe that's fundamentally uncertain, where the future is not fully determined. Fifth, the confirmation of bubble collisions would have philosophical and even theological implications. For millennia, humans have wondered whether there are other worlds, other realms of existence. Most religions and philosophies have posited something beyond our immediate reality, whether it's Plato's realm of ideal forms, Hindu and Buddhist cycles of creation and destruction, or the modern scientific idea of parallel universes. Discovering that other universes are real, that they can interact with ours, would vindicate some of these ancient intuitions. It would show that reality is far richer and more complex than the material world we directly perceive. At the same time, it would reinforce the scientific worldview. showing that even the most mind-bending ideas can be tested and understood through observation and reason. Would it change how we see ourselves? Maybe. Knowing that we're in one universe among countless others, that our Big Bang was just one of an infinite number, might make us feel even smaller and more insignificant. Or it might make us feel connected to something larger, part of an unimaginably vast creative process that's constantly generating new realities. Different people will react differently, but one thing is certain. If universes collide, and we have evidence of it, the world will never look quite the same. Every time we look up at the night sky, we'll know that beyond what we can see, beyond the most distant galaxies, there are other skies, other universes, some of which have touched our own and left their mark. Not everyone is convinced that the anomalies in the CMB are evidence of bubble collisions or any other exotic physics. Many scientists are deeply skeptical, and their criticisms are worth taking seriously. Science progresses through debate, through challenge and response, and the multiverse hypothesis has faced plenty of both. The first criticism is statistical. When you analyze a large data set looking for patterns, you're bound to find some things that look unusual just by chance. The more patterns you search for, the more likely you are to find false positives. This is called the multiple comparisons problem, or the look elsewhere effect. Researchers try to account for this by calculating appropriate p-values and significance levels, but there's always subjectivity involved in deciding what to test and how to interpret the results. Critics argue that the bubble collision researchers are cherry-picking features in the CMB, finding patterns that match their expectations and ignoring the thousands of other patterns that don't. Defenders respond that they're using rigorous statistical methods, comparing the data to simulations that include random fluctuations, and that the significance of the anomalies has been confirmed by multiple independent analyses. But the debate continues with no clear consensus. A second criticism is that there are always alternative explanations. For any anomaly in the data, you can usually construct a mundane explanation if you're willing to adjust your models or assumptions slightly. Maybe the cold spot is caused by a supervoid, or by a particular realization of the random fluctuations from inflation. Maybe the hemispherical asymmetry is due to how we define our coordinate system or remove foreground contamination. Critics argue that invoking other universes is a last resort, something you should only do when all other explanations have been exhausted. And we haven't exhausted the mundane explanations yet. There's still plenty of room for subtle effects, unrecognized systematics, or phenomena we haven't thought of that could explain the anomalies without requiring anything exotic. Defenders counter that the mundane explanations are becoming increasingly contrived, that you have to stack up multiple unlikely coincidences to explain all the anomalies without invoking new physics. At some point, Occam's razor cuts the other way. The simplest explanation might be that something genuinely new is going on. The third criticism is philosophical. Some scientists argue that the multiverse, and by extension, the bubble collision hypothesis, is not scientific because it's not falsifiable. If every possible observation can be accommodated by invoking some appropriate properties of other universes, and the theory makes no real predictions and can't be tested, this is a serious criticism. Falsifiability, the principle that a scientific theory must make predictions that could be proven wrong by observations, is a cornerstone of the scientific method. If a theory is flexible enough to explain anything, it explains nothing. Defenders of the multiverse hypothesis argue that it is falsifiable, at least in principle. If we found evidence that contradicted the predictions of eternal inflation, like certain patterns in the CMB that couldn't arise from any bubble collision scenario. That would falsify the hypothesis. The problem is that the predictions are not yet precise enough because we don't fully understand the physics of inflation and bubble formation. But this is a technical problem, not a fundamental one. As our theories improve and our observations become more detailed, the predictions will become sharper and the hypothesis will become more testable. Science doesn't require that every question be answerable right now, only that it be answerable in principle. A fourth criticism comes from the fact that we only have one universe to observe. In most of science, you can do experiments, test ideas multiple times, gather statistics. But with cosmology, we only have one cosmos, one CMB, one realization of the initial conditions. This makes it hard to distinguish genuine signals from random flukes. If we had 100 universes to observe, and we saw collision signatures in 50 of them, but not the others, we could be confident the signal is real. But we can't do that. We're stuck with the data we have, and we have to make the best inferences we can from it. This limitation is inherent to cosmology, and it means we have to be extra careful about our conclusions. But it doesn't mean cosmology isn't science. It just means it's a different kind of science, one that relies heavily on theoretical models, statistical reasoning, and indirect inference. Finally, there's a sociological criticism. Some argue that the multiverse has become fashionable, a bandwagon that researchers jump on because it's exciting and gets attention. Papers about the multiverse are more likely to be published in high-profile journals and covered by the media than papers about mundane explanations for anomalies. This creates a bias, a tendency to interpret ambiguous data in favor of the exotic hypothesis. There's probably some truth to this. Science is done by humans, and humans are influenced by social factors, by what's trendy, by what will advance their careers. But science also has self-correcting mechanisms. Other researchers scrutinize claims, try to replicate findings, propose alternative explanations. Over time, the truth tends to emerge, even if the path is messy and includes false starts and overhyped announcements. The bottom line is that skepticism is healthy and necessary. Extraordinary claims do require extraordinary evidence, and the evidence for bubble collisions is not yet extraordinary. It's suggestive, intriguing, tantalizing, but not definitive. More data, better analysis, and time will tell whether the hypothesis holds up or falls apart. We've reached the end of our journey through one of the most unsettling and exciting frontiers of modern cosmology. Let's take a moment to step back and see where we've been and what it all means. We started with the cosmic microwave background, the baby picture of the universe, and the strange anomalies that scientists have found in it. The cold spot, an inexplicably large and cold region that shouldn't exist according to standard models. The hemispherical asymmetry, a violation of the principle that the universe should look the same in all directions. The axis of evil, a mysterious alignment of the largest patterns with each other and with our local solar system. And the low L anomaly, the puzzling smoothness of the universe at the largest scales. These anomalies are real features of the data, confirmed by multiple satellites and independent analyses. They might be statistical flukes, but as more data has come in, they've persisted. They demand an explanation. We explored the concept of the multiverse, the idea that our universe is just one bubble in an eternally inflating sea of universes. This isn't science fiction, but a natural consequence of our best theories of the early universe. If eternal inflation is correct, bubble universes are constantly forming, each one a separate cosmos with its own Big Bang, its own history, possibly its own laws of physics. And if these bubbles are forming and expanding, they must sometimes collide. When they do, the collision leaves a signature, a pattern imprinted on the structure of each universe. Theoretical physicists have calculated what these signatures should look like, and they match some of the anomalies we see in the CMB. Teams of researchers have searched for collision signatures, using sophisticated algorithms and statistical methods to scan the data. They've found candidates, circular patterns, and unusual features that could be evidence of impacts from other universes. The evidence is not conclusive, but it's intriguing enough to justify continued investigation. We looked at the physics of collisions, what happens when two universes touch, and how the shock wave from the impact propagates through space, affecting matter and energy, leaving permanent scars that we can potentially detect billions of years later. We discussed connections to other mysteries, like dark energy, the Hubble tension, and the search for gravitational waves from the early universe. We saw how observations in multiple domains, from the CMB to galaxy surveys to gravitational wave detectors, might eventually converge to paint a coherent picture. We contemplated the implications. If universes really collide, it confirms the multiverse, teaches us about the physics of the very early cosmos, potentially explains fine-tuning problems, and fundamentally changes how we see our place in reality. We're not just in a universe, but in a multiverse, one bubble among countless others, some of which have touched us and left their mark. And we examined the criticisms, the skepticism of scientists who think the evidence is insufficient. The anomalies are statistical flukes, and invoking other universes is premature or even unscientific. These criticisms are important. They keep us honest, force us to be rigorous, ensure we don't get carried away by exciting ideas that aren't supported by the data. So where does that leave us? The honest answer is, we don't know yet. The data is suggestive but not definitive. The anomalies are real but might have mundane explanations. The theories are elegant but not yet precise enough to make unambiguous predictions. We're in a state of uncertainty, which is both frustrating and exhilarating. This is how science works at the frontier. We gather data, propose theories, test them, revise them, argue about them, and slowly, painstakingly, move toward the truth. Sometimes the process is fast, with a clear discovery that settles the question. More often, it's slow, with decades of incremental progress, false leads, and gradual convergence on an answer. The question of whether universes collide will likely take years, perhaps decades, to resolve definitively. We need more data from future satellites and telescopes. We need better theoretical models that make sharper predictions. We need breakthroughs in our understanding of quantum gravity and the physics of the very early universe. We need a bit of luck, a smoking gun signature that's unambiguous and impossible to explain any other way. But even if the answer turns out to be negative, if the anomalies are eventually explained by mundane physics and there's no evidence of collisions, the quest itself is valuable. It pushes the boundaries of what we can observe and understand. It forces us to confront the limits of our knowledge and imagine possibilities beyond our everyday experience. It reminds us that the universe is under no obligation to conform to our expectations, and that reality is often stranger than we dare to think. And if the answer is positive, if we confirm that universes really do collide, that our cosmos bears the scars of impacts with other realities, then we'll have taken one of the greatest steps in human understanding since we first looked up at the stars and wondered what they were. we'll have discovered that we're part of something unimaginably vast, a multiverse of infinite creativity and possibility. We'll have found that we're not alone, not in the sense of finding aliens, but in the deeper sense of finding that reality itself is far richer than we thought. There are other universes out there, other realms, and they've touched us. We carry their imprint in the very fabric of our cosmos. That's a humbling thought. It makes us small, insignificant in the grand scheme of infinite creation. But it's also inspiring, because we, tiny creatures on a small planet, are able to figure this out. We can look at subtle patterns in ancient light and infer the existence of other universes. We can use mathematics and physics to understand phenomena that dwarf our imagination. We can ask the deepest questions and have a reasonable hope of finding answers. So we wait. We watch the sky. We analyze the data. We refine our theories. And we wonder, do universes collide? The new data is disturbing, puzzling, fascinating. It's not giving us easy answers. Instead, it's giving us something more valuable, better questions, deeper mysteries, and the tantalizing possibility that the truth is far stranger and more wonderful than we ever imagined. The cosmos is speaking to us, whispering secrets in the faint patterns of ancient light. The question is, are we listening carefully enough to understand what it's trying to tell us?